Okay, geographers, we're going to get into water today, and this is the first lecture in this second section of the course. So we're going to get into the water itself today, but the atmosphere and climate and mainly atmospheric stuff. So we're going to be talking about water's connected to that, although not all the time absolutely. The connections will hopefully make sense as we get going. But just keep that in mind. As you're listening to this, you should have already finished your exam, the first exam for that first section, which means that first section is done, right? We are done with it. We completed that. We're now moving on to new things. So, keep that in mind. Another thing, too, I'll let you guys know, is that as I'm recording this, it's actually after some of the stuff that you're going to hear in the next, few lectures from now. And that has to do with when the whole, COVID thing really took off here in this country, when AVC made the decision to switch to online or remote or whatever, however we're phrasing it for that teaching. So I want to say it's like that modern climate lecture is the very first one that I recorded in this capacity. And I'm not going to go back and re-record any of that stuff, even though those first ones I recorded, I felt like a moron just talking into my computer. And I still feel that way, not having students to talk to and all that, but at least it's getting more normal. So I think these are less bad than some of those first ones. So it might not be as smooth as can be. I might also say ridiculous stuff during that, based on I don't know, I guess it was in March or April or whenever when I first recorded that stuff of 2020, right when all this is going down. I have no idea what I'm talking about. If I have words of hope like, this coronavirus thing, it'll probably pass. We'll be back in class by May. I don't know. So just keep that in mind as you're listening to it. Now, what I'm actually discussing there, all the geography stuff, that should be fun, right? So that's what I'm saying. And I say should be. I don't go back and listen to this stuff at all. God, it sounds awful to listen to yourself talk, for any period of time. So I don't know. If you guys have any questions with that stuff, these later lectures, or if something isn't totally clear, let me know. As always, it's up to you guys to communicate with me if something isn't making sense, and I will do everything I can to make sure the stuff makes sense. You dig? Okay, all right. So today, you're going to get into water and what it is. And so I have on the first thing here, this physical properties of water. We're very briefly going to discuss that nerdy, H2O chemistry stuff, because honestly, it's not that interesting compared to, basically what we can say is the spatiality of water, right? Again, we're in a geography class. We're into spatial analysis and relationships and all that. So we're going to spend more time talking about where water is and how space and place and all this stuff plays a role in our own water supply. Then we're going to get into, like hydrogen bonding and all that. Ugh, boring stuff. Sorry, I fell asleep there. No offense, chemists who love to discuss such things. All right, so let's start off with how we got water on our planet. And the thing is, it's been here since day one. So if you remember back to the planetesimal theory, which I discussed, I don't know, whenever I discussed it, in the last section, it's that whole idea of having the nebula and the sun condenses and all this debris starts smashing together and our planet and other planets form from that, right? And so the idea is, as that's happening, we've got water here, okay, right off the bat. And it's coming from, well, we have icy comets that are so bringing water to the planet, and we also have hydrogen and oxygen bonding together as stuff is getting smashed together and forming here on the planet, right? So from the beginning, 4.6 billion years ago, the Earth had water. Okay? Water was here on the planet. Now, the crazy thing is that the planet wasn't the same. So, how we think of water, that's a little different. Now, one thing that's happening is a lot of this water that's inside the Earth, because the Earth is so hot, it's doing what we call outgassing, which is what we see this with uh, geysers, things like Old Faithful, Yellowstone, right? When you have water erupting out of the Earth, that has to do with water getting heated up, right? It evaporates, so it's a vapor or a gas. It's rising, and as it erupts out, it returns to liquid form. But it's this convection idea of hot stuff rising, cold stuff sinking, right? So a lot of this water, it starts out here, it's in gas form, and it's coming from out of the Earth and up into the early version of the atmosphere, right? But here's the crazy thing. So this stuff goes up into the atmosphere. We're going to have condensation, which is the fancy way of saying clouds form. The water rains back down to Earth, but the planet is so hot that water immediately evaporates, right? Because it's just so hot from all of the smashing together, this violent collision that is making the planet. And so it's not until roughly 3.8 billion years ago that the surface of the Earth drops below 100 degrees Celsius, or below the boiling point of water. Right? So think about that. The Earth is 4.6 billion years old, and it's about the first billion years of its existence. It's too hot for liquid water to exist. Right? So it will, prior to this, will just evaporate back up, rain back down, evaporate back up, and so we don't have oceans and rivers and lakes and stuff like that, until about 3.8 billion years ago. And this number, don't stress over this. There's actually some work being done that might change this number right here, and we'll talk more about that when we get into geology and the idea of absolute and relative dating and how we do this stuff. But folks are constantly studying these different things, and we're refining ideas or supporting them, changing them, whatever. So don't get too hung up on that. But it's good to know. Yeah, we got we got water on Earth from the beginning, but it's not the same thing as we think of it. It's not water in the same way we think of it, or the Earth doesn't look the same way. And even once it cools down, I would imagine it's not like we suddenly have, gorgeous oceans and scenery and stuff like that. I would imagine that we've got, smelly, gross water, minerally stuff. You look at an image like this. I stole this one. This one I think is from Yellowstone, but there are other places around the planet that have these areas of geothermal activity where you have a lot of magma up close to the surface, and you have these hot springs that they could just be, just look like this. So even once we start to have water, liquid water accumulating on the surface, it's not how we might even think about it. All right, so water from the beginning, but different, if that makes sense. Now, and this number, this is good. This is when it becomes, important here. It's the idea that 2 billion years ago, water becomes a constant thing on this planet, meaning we have the same amount of water all over the planet at any given time, and it's been like that for the last 2 billion years. Okay? So we'll get into this, I'll talk about drought in a bit, and we hear, if my Californians to whom I am speaking, how are we doing with water these days? Are we good? Actually, that's maybe one thing, one good thing about all the chaos that's gone on in the last year is we haven't been thinking about the fact that we're also in a drought and thirsty and desperate for water and all that, right? We've kind of forgotten about that because of other issues. But yeah, and we'll see. Still in a drought here in California, been in a drought for a long, long time, technically. So, we have no water, right? But that's not to say that the earth is running out of water. It's not a case that, we're losing water. We got to find water on some other planet or whatever. The earth has plenty of water and always has plenty of water for we humans. It's an issue, though, of, where is that water, right? It's a spatial issue. So if we've had the same amount of water every day for the last 2 billion years, means when we have a period of drought, it's a case of the water just isn't where we want it. All right, we don't have water in California, but at the same time, we've got places that are dealing with flooding and record water amounts and all of that. Right? So it's a spatial issue. It's a distribution thing. So that's why this idea of having the same amount of water on the planet for the last 2 billion years, that's a key concept here because it helps us explain other stuff that's going on. And we'll talk specifically about California, but from a global standpoint, we look at what we call eustasy, which is referring to sea level change. Yeah, we tend to think of sea level as just, zero. That's the bottom, right? Because it's how we measure our elevation. But honestly, sea levels, those are averages of averages, and oceans aren't all at the same level. Like the Pacific Ocean and the Atlantic Ocean are at different levels, technically, even though we just call them zero. And so that has to do with all sorts of averaging that's done. But what we do, we're not looking at elevations, is we study sea levels and look at how they've changed over time. All right? And so it's the idea that sometimes in the Earth's history, ocean levels have been higher, and then at other times, ocean levels have been lower. I just, think for a moment, what are we going through right now? What's the state of the Earth's oceans? Are the ocean levels higher or lower than they have been in the, recent past? And you hopefully are answering higher, right? Our ocean levels are rising. And so that actually means something because of this idea that the Earth has the same amount of water and has had that for the last 2 billion years, right? Because if water is rising in the oceans, that means it's going into the oceans and it's not in other locations, right? And it has to do with temperature and it has to do with glacial ice. So glacial ice, and we'll talk about glaciers down the road, but that's a case of water being frozen and specifically frozen on land, right? So when it's colder on the planet, we have more water stored in glacial ice. And as a result, that means we have less water in the ocean. So in a period of an ice age, say that would be an extreme example of this, we would have way more water in glacial ice than in other times. And that means we have lowering ocean levels. But as the Earth starts to heat up, the glacial ice melts, that stuff flows downhill, and eventually that water will make its way out into the oceans. And so those ocean levels rise. And we'll also talk about this whole idea of, climate change, natural versus anthropogenic, which is a fancy way of saying human caused. We'll cover all that when I talk about climate change, because that is an important distinction, just like what I'm talking about right there. How, we have ice ages, cooling periods, and warming periods, and all that. People have conflated this idea of the Earth naturally going through climate fluctuations with the idea of we humans screwing up the planet, right? And they say, like, what, it's not us humans, because, the Earth changes and it heats and cools all the time. All right, people will say that. And while it's true that the Earth does go through these heating and cooling processes, it's incorrect to say that that's why we humans are doing nothing. It's actually a case of both are correct. The Earth naturally goes through changes, and as we'll see, and as I'll talk about, yeah, it naturally does that. We've actually screwed it up so much that we're breaking some of the natural fluctuations and so on. So it's very clear that we humans do this. And so seeing these rising sea levels today, that's actually that we know that's the result of human activity. But we can also look back in time, go back millions of years and look at past sea levels and get a sense of climate, and that's how we record a lot of this stuff. And again, we'll spend more time on that when we get into climate and climate change and so on. And now this image, there are a variety of things, and I have like a YouTube link here for a video that goes through this, and you can find a lot of this stuff out on the web, and there are different ways of doing it. And I'll just say, with these things, don't get hung up on the exact numbers, because everybody kind of does this a little differently. And so, everything's more or less the same idea. But I know students can get hung up. If you see like 97.2 here, and another one says 97.25, or some say 97.5, or whatever, like, don't worry about it. And what we're looking at here, here's what you should worry about. What this image is showing is the distribution, the spatial distribution of water on the planet, okay, currently, say. And so again, we have the same amount all the time, but it's really a question of where is it. And so if we look at the top here, let me get my laser thing. So this first line right here up at the top, we've got fresh water, 2.8%, ocean water, 97.2%. So this is 100% of the water that exists on the planet. Of all of the water that exists, over 97% is out there in the oceans. Okay? And that's a good way to think of it. Don't get hung up on like the 0.2 or whatever. Over 97%. All right, we'll just got to be broad with this stuff. That's a lot, right? So we've got tons of water on the planet from the, just from the start here, but the vast majority of it does not exist anywhere where it's actually useful for humans, like from a drinking water standpoint or a crop irrigation standpoint or whatever. Can we drink ocean water? No, right? Because of the salinity, because of the salt and stuff that's in there. So ocean water, completely useless, right? I mean, sure, you can go to the beach and play in it, and dolphins seem to like it, and we can take boats, like that kind of stuff. When it comes to life, supporting life, being able to drink it or grow food with it or whatever, garbage water. So you can see right off the bat, what exists for we humans is pretty small, right, in the grand scheme of things. And I'll also say, with this, because some of you listening might be saying, but wait a second, I thought there was something we could do to ocean water to make it so we can drink it. Yeah, technically, we have what's called desalination, where you can take salty ocean water and through whatever process, there are a few different ways to do this apparently, but through this process, you can get the salt out of the water and have fresh drinking water, which we can drink. And here in California, in thirsty California, this has been a thing. Like, people have said, why are we spending billions on this bullet train from LA to San Francisco? Let's take that money instead, put it into these desalination plants, and that way we solve our water crisis, right? Which right there, that sounds like a legit use of money. That sounds like a smart thing to do. The problem is that with these desalination processes, we have yet to really figure out a good way to do it to ensure that California's ecosystem won't be destroyed in the process. All right, like, this is done. Desalination is done. It's done on cruise ships and naval vessels and that kind of stuff to a smaller extent. It's also done in the Middle East. I think Saudi Arabia gets, like 100% of its drinking water from this or something, pretty close to 100. So that's, it's working in some places. The problem, though, is that when we go through and do it, as we pull out the salt from the water, what's left behind, it's not just like, crystallized solid salt. It's actually, we have fresh water gets extracted, and then the waste product is this unbelievably salty water, right? So we don't get 100% of the water out. It's just this very, very salty mixture that's left behind. And what we do is we put it back in the ocean, right? Because it came from the ocean to start with, so why not just dump it back into the ocean? It's salt. What's the big deal? And of course, the problem is it's so concentrated now that we're making the ocean saltier. Now, if it's on a small ship and doing this, the idea is, well, it's in a small local area and it's not going to affect the entire ocean. But if we start doing that all along the coast of California, if we start consistently increasing the salinity of the coast, that could wipe out all sorts of plants and fish and mammals and stuff like that. It's going to be a real bummer when we have dead sea lions and dolphins and stuff like that washing up on the beach. So that's why we don't do it. And you could say, like, okay, but in the Middle East they do it. But in the Middle East, the salinity is already a lot higher. And I'm ignorant in terms of, what it's doing to the oceans over there. But because of the temperatures and the confinement of like the Red Sea and the Persian Gulf, all these areas over there, they're much more spatially confined bodies of water. And so there's already kind of high evaporation. It's got a higher salinity than the Pacific. So we don't want to just look to these other places and say, well, if they do it, we can do it. We need to be aware of what's unique about California and our geography, right? So it sounds good to invest in this desalination stuff, but honestly, we don't know what that would do. And we could wind up, we get some water, short term, but in the long term, we could actually destroy this state from a natural standpoint. So we don't want to do that. Okay, so what that means is we've got this little amount of fresh water left. Now, if we work down here, we can see this fresh water, how that breaks down. And of this 2.8%, whatever, a little less than 3%, most of that is in ice sheets and glaciers. Okay? Meaning it's frozen in glacial ice. Again, something we'll talk about and truly define down the road. But that stuff is frozen and locked into place on land. Now, and one thing in talking about this with students before, I asked some of you guys, like, in classrooms in the past, like, and you guys remember visiting the Palmdale Glacier, like in high school or whatever, you go on field trips, saying this, and most students would go, wait, no, that doesn't make sense. And of course, the joke is, no, there's no Palmdale Glacier, right? We're in the hot desert. We're too hot and too low in elevation. We don't have glaciers out here. And I stopped doing that because one year, bless his heart, some guy very, like, just, I guess, wanting to please or whatever, just said, oh, yeah, I remember. And then made it really awkward to let him know, like, no, you don't remember. So I don't bring it up in quite that way, but just think about it, right? Where's the nearest glacier? Like, we've got a few teeny tiny ones, like in the Sierra Nevada, but still not of any real use when it comes to drinking water, right? Or irrigation water or whatever. This stuff is up in the Arctic or down in the Antarctic, miles and miles away from us. So honestly, I'm thinking of this as a Southern Californian, these ice sheets and glaciers, useless, garbage, right? So again, tiny amount. And we'll talk about groundwater in a moment, and that's exactly what it sounds like. It's water that's in the ground. This can be useful, though we got some issues, again, from a California standpoint, so we'll talk about that. And then we see this tiny little sliver, and this is showing the stuff that quite often we think of in terms of, what's useful as a drinking water resource, right? Rivers, freshwater lakes, stuff like that. Tiny, tiny amounts. I mean, look at rivers as a percentage of all of the water that's out there, incredibly minuscule. And you can think, having, if you've, been to an impressive river or driving around this country, you can cross stuff like, not too far from here as you go into Arizona, you cross the Colorado River, and that looks like a pretty good sized river. If you've ever driven, across the country, at least into Louisiana, you can, go over the Mississippi, which is a pretty amazing thing to do to see how massive that is. But then you also realize, actually, compared to all of the water that's out there, this is nothing. This is a tiny, tiny amount. So again, the Earth has plenty of water. The problem, though, is none of it is where we want it to be. We're in a capacity, that we want it, where it's, liquid and fresh and all of that stuff. So really, rather than, great. If people are going to be out there researching desalination and ways to make this less harmful, fantastic. We should continue to do that research. But honestly, until that time, maybe what we should be doing, if we're concerned with water, is being more intelligent about how we use it, right? Not waste it. Things like having, green lawns here in the Mojave Desert, kind of a weird concept. And it's us just trying to be British. I mean, that's really what a lawn is in this country, where we're hung up on still being British, even though we fought a Revolutionary War and all that. But it doesn't make sense here, right? Or looking at the agricultural crops here in California, the stuff we grow doesn't necessarily make sense to grow here in California. Yeah, we can do it maybe, but it requires a huge amount of water to do that. So really, when it comes to water resources and dealing with drought and all that stuff, just keep this in mind, right? We don't want to wait for a technological fix. We should instead be conserving what little water we actually have. Because if we do that, we'd be totally fine. The whole drought thing doesn't have to be as scary as it is. It's not to minimize it, because there are clearly issues, and we'll talk about drought in a bit. But just keep that in mind. The best way to, have water here in California is to not constantly throw it away or waste it in a way that's really not helpful to life, or not a smart way to use it to keep us alive, right? That's just, something to think about. All right. Now we're a science class, damn it. So let's do this. We got the H2O, hydrogen, oxygen. Oh, so boring. Like, we know this, right? This is one of the first things that we learn. And honestly, the chemical composition of water, nowhere near as important as the other stuff we're going to get into. And if you see this and you're like, all right, that's my jam, great. Become a hydrologist, take some advanced classes. You can do all you want with this stuff. Really, the only thing important here with water is that, and with the actual chemistry of it, is that the bonding, the hydrogen bonding that occurs, helps to make water a very stable thing on this planet. And like chemists, I know I've heard of, hydrogen bonding is not the best kind of bond or whatever. Blah, 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 blah. I don't care about that at all. What's great about this is that water, just the way in which hydrogen and oxygen bond together to form water, it's stable. Water wants to stay together. It doesn't want to dissolve, break down, turn into something else, right? The hydrogen and the oxygen atoms here want to stick together and make up these water molecules and continue to do that. And so because of this, water is what we call a solvent, meaning it's able to dissolve other things. All right, so solvent is a term we use to describe, like Windex and household cleaners, the stuff you spray on something that's tough on grease or grime or whatever. Like the idea, it's a solvent, meaning it breaks apart the grease, grime, that kind of stuff. right? Water is a natural solvent, and that will actually become important as we look to other stuff. When we get into geology and geomorphology, and we see how water is able to just, destroy stuff, but in a cool way. Like, it's why we have the Grand Canyon, right? Some of these impressive landforms. It's because water is able to, you know, get into the rocks and all that, break it apart. Water doesn't actually fall apart, right? Or it's able to carry acids and other stuff with it that help to break apart rocks or whatever it is it's running into. And that's why also we don't find pure water out in nature, or if we do, it's not for very long. And that's because it's got stuff in it because it's breaking things down. Right? So some water in nature is cleaner, more drinkable than other water, but it's not like we got to get out of this idea of pure H2O. That's not even necessary, and that's not even a natural thing, right? If that makes sense. And again, we'll talk about that stuff more, right, down the road. Energy stuff. No, we're gonna. You know what? Let's skip all that. Let's get here. Here's the good stuff. And we're gonna die of thirst. This is the stuff that we care about, and I say we as just being average, normal human beings. Right? It's great. Like if you're excited about how water works and moves and weather patterns and stuff like that, fantastic. Some of that stuff is kind of cool, but really, what we should focus our attention on here, and especially in a 101 level class, is this kind of stuff. So I have two images right here, stole these, and these are of the Hoover Dam, if it's not clear. So a dam along the Colorado River just outside of Las Vegas, and the dates here, we have 1983 and then 2007, taken at effectively the same location, and we can see two dramatically different moments, right? This top one in the 80s, this is during an El Nino event. And El Nino, we're not going to dwell on that in here, but it has to do with, well, it's the Pacific Ocean. It heats in a spot where it's not supposed to, and that flips stuff around. And the result is here on our side of the Pacific Ocean, like in California, we have more rain than we normally would. So it's a wetter year when we're in one of these El Nino periods. And it's a natural thing. It's not something humans are doing. We don't even fully understand why it does this. We just know it happens. And so in the 80s here that we see the full Colorado River, it's because we had a lot of rain. We had an abnormal amount of rain falling down. So the Colorado River is full. And this was actually a case where there was concern that the Hoover Dam was going to fail because so much water was coming through here. It wasn't looking like it was going to be able to, hold it all. So we had to get rid of a lot of it, flush it out to protect, Las Vegas from getting just washed away, right? Think about that however you want, the biblical ramifications of that and all that. But no, we flush all this stuff out to maintain, tolerable levels of water behind the dam right here. And the Colorado River runs out into the Gulf of California or Sea of Cortez, depending on, which side of the border you're on there. But the body of water between Baja California and the rest of Mexico, right? So the Colorado River naturally heads out there. So all this water, this extra water, we get rid of it. We send it out into the ocean, right? To save precious Las Vegas. Then we move forward in time. There's 2007. This is during a drought, obviously, but as we'll see, we haven't ever really truly stopped living in this drought, right? So over a decade ago, this is what the Colorado River looked like here at the Hoover. But honestly, we've had better years and worse years, but we're still dealing with these drought conditions. And what's really frustrating, well, this is kind of the new normal right here, right? But that when we have these periods of, extra water, we just flush it away, right? And then when we have periods of no water, we go, man, sure could use some water. not thinking long term. Now that's kind of unfair because I mean, like the people of Las Vegas and in Nevada and Arizona and these dry western states, a lot of them have invested millions of dollars into some groundwater storage facilities. So these artificial aquifers where they put some of this excess water in there and they're banking it, right? Banking a little bit of water here and there so that when we're in these dry years, we've got some resources, right? Again, and I say we, that's like for Phoenix and Las Vegas and some of those cities. They're doing it. Do we do this here in California? No. What are we, nerds? No. We'll be fine. We're Californian, baby. It's going to be okay. Yeah, this is, if anything, like all the people talking about desalinization and all that, like it would be wise to investigate in just, banking some water. And of course, you don't want to throw it all in there, and there are issues if we don't allow runoff. That's going to affect ecosystem stuff too, right? Like turn certain places into deserts and all that because we hoard all the water. So some of this has to go out to the oceans, but there could be this balance. But we don't think about that here in California. And honestly, it's something that we do need to be thinking about. Like, what are we doing with our water? Are we going to go for a strict conservation approach to just preserve what we've got, conserve what we've got, use just what's necessary, and be responsible with it? Do we need some kind of bigger engineering innovation? Like, what are we going to do? Right? That's something that's facing us here in the West. And again, it's a case of, it's not so much of, the earth running out of water. That doesn't happen, but it's a case of water isn't always where we want it to be. Okay? But then there are other places around this country and around the world where they've got plenty of water. You go into the eastern United States, drought has a totally different feel. Like I remember last time I was in, well, not the last one, a while ago, I was in Texas, in East Texas, where they get a lot of rain and, hurricane activity and stuff like that. And I was there one summer and it was during this drought period. But as a Californian, I thought that was the funniest thing ever because everything was still green. They still had tons of water and it was so humid and there was just water in the air and all of that. Their idea of drought, like technically it fit the definition, but we would kill to have those East Texas drought conditions just because it was way more water than we would even normally see over here. But for there, relatively speaking, it was a drought, right? That's the idea. But then in this area where they've got tons of water, well, they pollute the hell out of it, so it almost doesn't matter. And this has been a real issue, and it's most notably, Flint, Michigan was the most notable example of having water that's so full of all sorts of crap that you can't drink it because you'll get poison, right? And it turns out a lot of this stuff has legally been something that's been okay to do. Like it ain't no thing to legally pollute water because of the way our laws are set up and the way we just treat the environment here in the United States. And so this is from a New York Times article that was reporting on this stuff a while ago. Now, I think this was like 2010, for when this was actually happening here. But it was a case of the Clean Water Act, which was a great moment in American history. But it turns out the Clean Water Act wasn't all it could have been, right? Or people have found some loopholes. And this Clean Water Act and the Clean Air Act as well, these things happened in the 70s, and it was in response to certain bodies of water here in this country catching fire. Right? Let's think about that. And I know I skipped through like the chemistry of water, but you guys are aware, right, of the fact that water should not catch fire. We get that? We down with that? Is that clear? And of course, it wasn't the H2O that's bursting into flames. It's all the crap that we had put in the water that was, bursting into flames. So as a country, we're looking at our flaming bodies of water and we go, that's not good. that's unfortunate. And we're kind of thinking too, like, man, don't we need water to live? Yeah, this is not good. So as a nation, we come together and form the EPA, and we decide, hey, and this is really bold decision making here. We say, hey, let's not put crap in our water. Right? There was a time in our country where we could come together and say, yeah, that's bad. Let's not do that. Right? Um, we don't do that anymore. And case in point, with this 2010 issue here, it was a case of people realized that, oh, the Clean Water Act is only written to protect really large bodies of water, right? So, like a main river, one that you actually navigate, ships and barges and stuff up and down, like the Mississippi River itself, that's protected because that's a big one. It's a waterway that is used for transportation, and therefore we're going to protect that, right? And then if it's a tiny little creek or whatever, then where we don't not taking ships up and down, it's not used for like capitalist transportation, moving goods and stuff like that. Well, then it's not under the Clean Water Act, meaning legally, if you own the property around this thing, you can dump whatever the hell you want into that water, even if that little creek runs into one of these protected bodies of water, doesn't matter, right? And it unfortunately kind of shows how a lot of this stuff is written. It's to protect businesses, and it was really to make sure. It wasn't the fact that we had flaming bodies of water. It wasn't like, man, that's bad for our health. It was more of, how are we going to move stuff to sell and use for manufacturing and all that up and down the river, right? That was the issue. It was to protect profits, and so no shock. This is why these little things aren't protected. So a real issue, and this one in Alabama, saying pipe makers dumping oil, lead, and zinc. Nobody wants to drink this stuff, and that going back to Flint, the one where most of us are aware of, the real issue was lead in the water. I mean, it wasn't the only thing, but lead was the really scary thing. And that the Flint thing, I talk more about that in my cultural class. But it's a case of stuff that was going in to treat other nasty stuff. Was also degrading the pipes and letting lead get leached into the water itself, and then all sorts of people are just ingesting very toxic amounts of lead, and it's awful. I mean, it's the most vile thing in the world, especially when you realize that all these people in charge, who weren't elected to be in charge, they're actually forced into place. Again, there's a lot of cultural and political stuff there. But what happened with all these people drinking this lead, especially the kids, they're forever broken, right? Like permanent brain damage. That's how serious and severe this stuff is, where you have an entire city full of children who will never be the same and never live up to their full potential, all because some people were trying, again, it's a profit thing and trying to make some money, and letting poor people suffer as a result. So this is nasty, horrible, awful stuff, and we let it happen, right? And we should not let it happen. It is shocking to think that water, the most important thing for just life to continue, is something we rarely think about and don't actually protect. And you should also think too, one reason why this is so important is we can't have a substitute for water, right? Like it's the only thing on the planet where really, I mean, I guess, oxygen is another one of these things where we can't synthesize it in a way where we can make some alternative, right? Some water-like substance that isn't actually water, but it's something that we can instead just, use in water's place. Doesn't work that way. So we have to have water. I mean, sure, you can, make, hydrogen and oxygen bond together and all that, but that's beside the point. We need water, just plain and simple right there, to survive. And yet it's something we don't treat as like a right for people to have access to clean water in this country, right? You can instead buy bottled water or whatever if you got the money, and quite often that's just water that should be ours to begin with, and we're paying, like, it's a whole thing. Look, this is awful. I'm getting off on a rant. I'm gonna bring that back in. We're not here to fight the man yet. Let's get into some more science and spatial analysis here. Both of these things, whether it's the crap we're putting into water or the fact that we don't have any water when we want it in these drought conditions, they're both connected to what we call the hydrological cycle, okay? Which is just, it's a spatial thing. And quite often, like, students will, they hear this, the hydrological cycle, or it's called the water cycle as well. You hear that and you think, oh yeah, it's water freezes and it's ice and it's liquid and it's vapor. No, that's this phase change stuff. Don't get hung up on that. Even though that's, in a sense, it's part of this. But the hydrological cycle or water cycle, in this case, and what we're talking about in this class, is it has to do with how water moves, right, around the planet. Okay? And so what we're looking at, like, we're going to start with the ocean. And I should say, like, it's a cycle. So by definition, there's no beginning or end, right? It's a continuous thing. Yeah, that's by definition, that's correct. But we're going to begin and end in the ocean. Why? Because that's where all of the water is, right? And, over 97% is out here in the ocean. So we're going to start here. We're going to end here. So keep that in mind. So out here in the ocean, we got this water still out there. Some of that is going to evaporate, right? Meaning it heats up, converts into a vapor or gas, and works its way up into the atmosphere, which is what this arrow is right here. Now, what I want to point out is that this image here is important, if for no other reason than the fact that I used my incredible Photoshop skills to come in here and get rid of all these convenient labels, right? And instead of having things like ocean and evaporation and precipitation and all that, I have very Scantron-friendly letters, right? A, B, C. And on this second exam that you're going to have to take, you're going to have a few questions, just like you had with the first one with the public land survey system stuff. Same kind of deal here, but you'll see this image, and it'll be like, what's going on with this? And you'll answer A, B, C, whatever it is, right? So that said, just make sure you get a sense of what's going on here, right? What is in fact happening here, so that when you're faced with this and I ask you a question, like, where does this begin and end? You could answer the ocean, whatever letter is there, right? That's the general idea. Okay. And also, that said too, just a reminder, as you're taking the second exam, I talked about this with the first exam, make sure you're using a browser that allows you to see images. Like Safari on Macs doesn't like Canvas. They don't work well together, at least not consistently. So if you're trying to do the test and, using Safari, you're going to see just blank, like a red X or whatever, and you're not going to be able to answer it. Firefox, Chrome, these things seem to work, but just, make sure. If you can already see images on Canvas, you're cool, but keep that in mind because that'll be part of your test. Does that make sense? Or if you're using the Canvas app, if you're doing this like on your phone or iPad or whatever, just make sure you can see all the images in the other part of Canvas. Okay, all right, so that's test talk. So we start in the ocean. We have this evaporation. Now this 84 centimeters per year, don't worry about these numbers because they're taken out of context, so they're not really useful in this sense right here. But what it's showing you, if you add this stuff up, it's going to equal 100%, right? So all of this water that leaves the ocean will eventually come back to the ocean, is what they're trying to do with that. But I'm not going to test you on these exact figures. Instead, I want to make sure you guys know the bigger pattern itself, right? That's the idea. So we have this evaporate. As it comes up, what's going to happen is condensation, which is cloud formation. And then from there, we'll have precipitation, okay, in this case, rainfall. So precipitation is our, general term for water falling from the sky. Rain, sleet, hail, snow, whatever, right? So we have these clouds form, and you can see, I mean, this is one case where the numbers are useful. Most of this water that leaves the ocean, it rains right back into the ocean, right? So this actually is one complete cycle in here, begins in the ocean, goes up in the sky, pretty much immediately falls right back into the ocean, right? So most of this water out here, it's stuck in the ocean, and again, it's useless to us. It's of no value for us to drink this stuff. But there's a little bit of this stuff that blows on land, okay, which is what we're seeing right here. So this transport by wind. We've got this moisture-bearing air. There's water vapor in here. There are rain clouds in here. That's going to move onshore, right here, onto the continents. Okay, and as that's moving on, we also have what's called Vapo Transpiration right here, and I'll fully define that in a moment. But it's like, for now, we can just think of it like evaporation. So we have more water coming up into the atmosphere and condensation taking place. So this and this are going to, join together, and it's going to lead to precipitation for the continents, right? Rain or snow or whatever that falls on land. And that precipitation that happens over here, that is our only input of new water, right, for us to use, right? So that's why, like here in California, we freak out. We get so excited when rain is in the forecast because it means that we have water coming in, right? It's there's no other way we're getting it, right? In the big picture sense of this stuff, we need precipitation to have this new input of water coming into our ecosystem, coming into California. So this stuff rains down, and then it's going to not just stay wherever it falls. Eventually, it's going to come back to the ocean, toward the ocean. And that's what this runoff is right here. So that's meaning stuff that falls and goes into, a creek or a lake or a river or whatever. All of this stuff is going to eventually flow downhill and work its way back to the ocean, right? And it may, on its way down as runoff, it can undergo this evapotranspiration again and go back up into the atmosphere, and it'll rain down. And so it could be stuck here for a little bit, but eventually everything here on the continents, it's going to work its way back to the oceans. And the one thing this particular image doesn't show is that some of this too will go into the ground and become groundwater. Something we'll talk about a little later, but still, it's all eventually working its way back to the oceans. Okay? Hopefully that makes sense. It's not that crazy difficult to think about, but just kind of go through here. Make sure you understand what's happening. And I'm going to talk about evapotranspiration in a moment as I, advance to the next slide. So I'll get more into that. But hopefully this other stuff makes sense. And this is also why, with our political and legal discussions of where you can pollute water and can't and all that, that's why it's so stupid. Because all of this stuff is going to the same area, right? It's like if you pollute in this little tiny creek over here, it's all going to the ocean, and a lot of that little creek, it's going to flow to that bigger river that is protected, and it just means anything that's upstream, that's uphill, that is polluted, and while that pollution is going to be carried along, and it's going to pollute everything downstream, right? And eventually pollute the oceans if it's enough pollution, which of course in this country it's always enough pollution. So it's something we should be thinking about. It's pretty common sense when you think about it, even for just a moment. But we don't, or we ignore it, or we hope that everything will be okay. All right, so there's that, our hydrological or water cycle. Now let's talk about evapotranspiration. It's a combination of evaporation, which we get, water heats up, turns to vapor, goes up into the sky. But then it's also what we call transpiration, which is how plants use water. They bring it up, and not only are they using water to like bring nutrients and stuff into the plant itself, but they can also cool themselves and flush out water. It's like how we sweat. And this is what we call transpiration, and how this water vapor gets pushed out of the plants as a cooling mechanism and to get rid of excess water and all of that, right? And so we have water vapor getting into the atmosphere either through evaporation or through transpiration. And it's impossible to know when you detect water vapor in the air whether it came from a plant or just heat or whatever. So we just put it together. It's evapotranspiration. Okay, but what that means is where we have, precipitation is our input. And so on this I just grabbed this. I don't even know what Silver Lake is talking about. I just found it online and took it. It works. This blue line is precipitation. So that's our input, right? Any rain or snow or whatever that's bringing new water into this specific area. And then PE would be potential evapotranspiration. That's the output. That's us losing water. Because like with, runoff and stuff like that, that's okay. We can, dip into a river and use that. We don't see that as a true loss in the sense of water. But when it's converted to water vapor and just goes high up in the sky, that is a loss. That's not something that's easy for us to access. And so it's water leaving a place, right? And so this water budget idea, when we're thinking about water resources for an area, and therefore how big a city can get or a community can get, what kind of crops can be planted, that kind of stuff, we're looking into precipitation, how much water is coming in to an area, and then evapotranspiration, how much water is leaving an area, right? And you can see like what this is showing, this spike in evapotranspiration. It happens in the summer when it's hotter. So you have more evaporation, you have more hot plants that are, doing this transpiration to cool off. So you got more there. But then in the winter, it's going to be lower. And you just hope from an annual standpoint that you have more water coming in than going out, right? It's the same thing with like a checking account. With money in general, you hope to have more money coming in than is going out, right? Not always the case, but to be successful, to be not panicking all the time, you want more input, less output, right? Same thing with water. That's the idea there. And to look at just, most of North America in general, this map is showing annual precipitation, meaning how much rain or snow or whatever falls throughout the year. And it's using this this color scheme where, the darker blue is 80 inches and above of rainfall. So we see that like in the Pacific Northwest up here. This lighter blue, 60 to 79 inches of rainfall throughout the year. Again, or snow or hail or whatever. So down here in the Gulf of Mexico, the Gulf states, Louisiana, Mississippi, Alabama, Florida, this area, 60 to 79 inches along the Gulf Coast. So that's a lot of water coming in. Now here in California, and these lines, they're kind of fuzzy because this little hump right here, that's the Antelope Valley, is what it should be right there, which should actually be more over to the west a little bit, but we fall into this area right here, which is under 10 inches of rain per year. We get about 6 or 7 annually in Lancaster and in Palmdale in the general area here. And that's why, we're dry. That's why we're a desert, right? We look very different from these folks over here. Now this map, for effectively the same area, shows annual potential evapotranspiration, meaning it's not just the evapotranspiration that takes place, it's what could happen, right? Assuming there was, enough water in an area, this is how much would disappear. All right, so going back here to these Gulf states that we're getting 60 to 79 inches of rain per year, they're in this yellowish color. Around 40 inches is lost to evapotranspiration. okay, throughout the year. All conditions being equal, all that stuff, which is fine, totally fine, because they've got, 60 coming in, 40 going out. Perfect. Plenty of water. Everything's cool. Then you come back here. We're also in this kind of yellowish thing, so we're about 40 inches as well. But this is where that whole potential idea gets into place. We don't have 40 inches of rain a year to lose, right? Because we only get about 7 coming in. So it's showing, really what this is showing is that only a fool would live in this part of the world, because we have no water coming in. And even if we had an incredibly wet and rainy year, like during these El Nino periods, it's not like we suddenly turn into this lush jungle or whatever. All that water goes away, right? Let's say we had an amazing year of 12 inches of rain. It would feel very wet around here. That's all going to be gone. That's not going to be a long lasting thing, because the summer comes, it's going to vanish, right? So that's what this is showing. These eastern states, yeah, they can have a lot of evapotranspiration, but they got way more rain, so they're cool. The western states, not so cool, right? That's the idea right there. So that's that's a concern, and that's also, say, this is normal, right? These are normal conditions. But then we have this idea of a drought, which means we have less annual precipitation than we would expect. Right? That's really all a drought is. We normally should get this much rainfall, this much snowfall in an area, but we don't. We get less than that, right? This annual potential evapotranspiration, that's not going to change. We don't have periods where that's going to be less. I mean, temperature fluctuations can change it, but honestly, if we're doing anything, we're getting warmer, right? So that's not helpful. And so that's why drought is such a concern, especially in a place like California. We're already dealing with deficits in a lot of places around the state. And then you're telling me that we have even less than we normally do. That's problematic. And we measure this stuff. We record drought conditions throughout the year, consistently throughout the year. And one thing I've done since I started teaching this class here at AVC, I've just been pulling each semester. I'm teaching the class. I've been pulling the U.S. Drought Monitor map, a day or two before that actual semester, and I've just put them in here. So you can see up at the top, September 9th, 2008, that was the first map that I grabbed, right? So we're going to go forward in time, get up to today, effectively, and get a sense of what California has been dealing with, right? So here's the state. If you guys aren't familiar with our counties here, this is Los Angeles County, right? So this is where we're at the moment, or at least where AVC is at. I don't know where you're listening to this stuff. We've got Kern County right here. The line, that's Avenue A in Rosamond, to give it some context right there. We've got Sacramento County is up here, right? So this is the state. Okay, this is what we're looking at. And then to read our legend right here, if it's white anywhere, which it isn't here, it just means there are no drought conditions, right? And then yellow is abnormally dry, like we see right here. So it means, yeah, it's a drought. It's not great, but it's not, life-threatening or whatever. And then this lighter orange is drought moderate, and the darker orange is a severe drought. So that's not good. I mean, you can just hear severe. That doesn't sound good. And then the red is extreme drought. And then this darker red is exceptional, which that makes it sound like it's, fantastic, which is not the case. It's not because it's a fantastic thing. It's simply, it's really bad, right? We should come up with a new term, because exceptional makes it sound like, way to go, team. And that's clearly not the case, right? But this is September 2008. So now we move forward to February 24th, 2009. Look, here's some good news, right? We got no drought down here. This abnormally dry, that's like better than, it was. And we're doing better in LA County. And I mean, there's this. up here, this extreme drought, but that's Northern California, baby. Why, who cares about that, right? Do we care about Northern California? Of course not. That's why we live down here in gorgeous Southern California. I mean, yeah, I got family up here, but they're dead to me. That's why I moved down here. As soon as I moved down here, sure, it was for a job, but still, I said, Northern California, you're dead to me. So, right, we don't care about them. So we're doing better. That's all we care about, right? Right. Is there any reason why we should freak out about this, other than just being a good human being and being like, human suffering is never good? Is there a more practical, selfish reason why we should freak out about this? Well, let's think about it, right? So we're saying, hey, great, like this area, hey, cool, no drought conditions whatsoever. But what does this look like over here? You ever been over here? How gorgeous are these forests? It's desert, right? This is all desert, and this is desert, and we're desert over here. So really, even in our best conditions, we got no water. So to say like, yay, no drought, still thirsty and dry and all that, where do we get our water from? Up here, right? We'll talk about the California aqueduct and how that works. But the reason we can exist here is because we've got a steady supply of water that starts up here and works its way down here and comes here to us. So this is actually way scarier. I mean, it's almost like, it's not exactly like this, but honestly, so we have, some drought, here in LA County, not a big deal because we import so much of our water, right? But that is problematic. But let's see, that's back in 2009. I'm sure we're fine. See, September of 2009, that's better. Hey, 2010, that's looking pretty good, right? I mean, yeah, we got some dry spots, but that's nothing. Nothing. Oh, look at that. Look at that. Do you guys think, can we pull this off, you think? What do you guys think? Are we going to do it? Are you ready? All right, go. Oh, my God. Oh, my God. Do you remember this day? April 5th, 2011, the day we beat the drought? Oh, I remember it. Such a great day. I just turned on every single hose at my house and all the faucets and all that stuff. Just let the water flow because we beat the drought. We did it. We finally did it. And it will never, ever, ever, ever come back. Oh, shoot. It's coming back, right? In October. And I always love this map. It looks like, where does it look like that drought's sneaking up from? Mexico, right? So I need to build the wall. I think that's why we want a wall. It's because of that pesky drought that keeps sneaking in. Yeah, do with that what you will. Yeah, okay. So, okay, we didn't beat the drought, but it's not too bad. I think we're going to be okay. Oh, damn it. Look at that. It's coming. But look, kind of looks like we have a wall right here. That it's all, the drought stuff is all in San Bernardino County, and we're okay. I think we're going to be okay. Shoot. No, it's here. And that red is sneaking in from Nevada. Well, we need a wall, a Nevada wall as well. We need walls all around to keep these droughts out. Okay, we're getting better. Got rid of that red, built the wall clearly up there. We're going to be, okay, damn it. Come on. Look at that. Now we're red right here. But again, like for us to have an extreme drought here in Rosamond, like I defy you to look around Rosamond and go like, boy, it sure looks drier than it did last year. It's Rosamond, right? It looks like Mars. And we'll see images of that later on. You'll see exactly what I mean when I say it looks like Mars. So yeah, okay, that's no good. Look at that. 2014. And this is, too, you notice, like, not only are we in that exceptional drought situation, which, right, doesn't mean it's a great drought. It means it's apocalyptic. That's what we should call it. Apocalyptic drought is the dark red. Not only are we have those conditions, but you can see they changed the format of the map, right? Like, to get us to wake up, to say, look, made California bigger. That's terrifying. And it didn't get any better anytime soon, and you just kind of use 2015. And there was a lot of this. It just kept going on and going on. And I don't know if you remember this period, but down here in Southern California, like the Antelope Valley especially, like the drought thing, we knew the drought was bad, but it didn't seem like, I mean, it's bad, but it's not ruining my day or whatever. But I would talk to family up north, and they were so depressed. Just like, oh my God, it's drought. It's all. I hope you're not showering every day. And and oh no, of course not. But I was, I sweat. But yeah, the people up north were really depressed. It didn't seem that bad down here. And then I realized when I actually drove up around this time, I go visit family in the summer. You're driving up, like usually, if you drive up I-5, you'll go through. You get to Bakersfield, and you'll go past some stuff, and it's brown and brown and brown, and then it starts to transition. You get up closer to like Fresno, and it starts turning a little more green in areas, and it will just continue. The green just gets darker and more more verdant as you get further north. Well, that green never showed up. Right? By the time you got up to like Sacramento, it's still brown and dead. And I realized, oh my God, the reason why everybody up north is so depressed is because they're starting to look like us, right? They're starting to look like the Antelope Valley or Bakersfield or whatever. And yeah, you can't blame them for being depressed. Where you go from lush green trees and stuff like that to just dead brown desert everywhere. But it wasn't something we really noticed. And I'll get into why that is too in a bit, but in part it's because of, we're already a desert. We're already dead and dry and brown down here, so we're not noticing it. But when you look at this, that makes you pay attention, right? And it continues. Here's 2016. 2016 again, it's at least looking better in the north. Hey, 2017. Look at you. Look at that. Oh, dang it. I mean, we were so close to beating the drought. But, that wall, again, need that wall right there. But hey, remember, this is what we care about. Up there, oh my gosh. Are we going to do it? Are we going to beat the drought? I think we are. No, we're not. And here we are today. Here's June 16th, 2020, the latest map. As I'm recording this, what you can see, I mean, with all this stuff, like to get excited, if we go back here to go like, whoa, we're okay. It's ridiculous. It's a long-term thing. These little snapshots in the drought maps, they don't really tell you anything. It's looking at that big scale stuff. So the good news is we haven't had these exceptional apocalyptic droughts in a few years, but we're not out of this. We haven't left the drought. You hear like in news media, people talking about, oh, good, the drought's done. Like, back in 2014, 15, 16, like that was a moment in time that we've left and everything's okay. No, we've been in this drought. I mean, think back to that picture of the Hoover Dam in 2007. We also were in drought conditions there, right? We started this in 2008 with these maps here, and you can see drought. That's just, it's almost to the point where drought is meaningless because we're always in a drought, right? It doesn't mean like, oh, that's unusual. We don't have as much water. It's a case of we just don't have water in California anymore. We're losing this water. Again, it's not the planet losing it. It's not here. And it turns out when we look at this stuff, we're not ever not going to have a drought. Like that's a part of California. The indigenous Californians were aware of this. It's always been the way this place has been. It has to do with its location and the cold California current and, the precise climate that's here and all that stuff. But this really scary once in a lifetime, hopefully once in a lifetime, but honestly, we'll see it again, at some point here. The reason why these droughts were so bad, or these, little moments in the drought were so bad, it's all because of anthropogenic warming, which again, anthropogenic, it means human caused, right? Anthropos, it's humans, genic, think like Genesis, creation, right? It's human caused warming, climate change is what we're talking about, saying the drought was going to happen. It's not that human caused climate change caused the drought to happen, but it definitely made it worse. All right, and we'll see examples of this in other places too. It's not just droughts, it's other stuff like the monsoonal rains in South Asia. They're getting worse. Like stuff is getting more extreme and worse, and it's because of us, and because we're not addressing climate change. So we'll talk about that too, but you can see our water completely connected to, natural, normal climates, as well as stuff we've been doing in recent years. Now, how do we deal with this? We need water, right? We got to find it somehow. So, how do we Californians deal with it? Now, traditionally, if you didn't live like right next to a river, your supply of water was going to come from groundwater, okay? Which, like I said earlier, is exactly what it sounds like. It's water that's in the ground. And so what this image here is showing, like this is a cutaway of the land. And if you were to, dig down here, you would find what we call an aquifer. In fact, I think, let me, move here. So these two terms here, we have aquifer, that refers to the actual collection of water stored in the ground. Okay? And this is a case of, it's kind of a hard thing to grasp or, visualize. It's not like we have a big cave or cavern or whatever, and there's an ocean underneath the, underneath the Antelope Valley or whatever. I mean, there are cases, we'll get into karst and caverns and, how water can be stored in that way. But in a place like California, it's not all like that. A lot of this is just, it's simply gravel. There's spaces in rock through which water can flow, and it just hangs out under the ground. It's protected from evaporation and transpiration and all that. And so we just have this collection of water stored in an aquifer, right? And then water table refers to that uppermost limit, the top of the aquifer. And that can change depending on time of the year, right? Like in a rainy time of the year, that water will, fall to the ground. It will infiltrate the soil, go down into the aquifer, cause the aquifer to grow, and therefore the water table goes up higher, gets closer to the surface, right? And then you have a period where there's no rain, or especially like a period of drought. People are still utilizing that aquifer, right? Using a well, right, to drill into that to take the water out of it, but there's not other water coming in, so that water table will drop as the aquifer gets smaller, right? Hopefully makes sense. And we, like here in the Antelope Valley in Southern California, we have places that rely on wells and groundwater and all this stuff. But like in the AV especially, no, it exists. Some people still use it, but it's not what it once was. In fact, we found out, like, we have aquifers here in California. We've trashed them. And I say we, like, it's not even a case of like, we did it or our parents did it or whatever. Like, you can go back, over 100 years ago, and this stuff was trashed. In fact, in California itself, the Central Valley had an incredible aquifer, just water flowing in to the into the Central Valley and going in underneath it into this big aquifer. And it was right after the gold rush in the 1850s, where you have a lot of people who come out here, try to make it rich with gold, doesn't work out. They instead get farmland in the Central Valley to try to, I'm just gonna, I'll just have a farm, I'll just survive in this way. And within about a decade, that groundwater is just gone, right? Like, it's still there, but it's not what it once was. Same thing here in the Antelope Valley. There was groundwater. It took hundreds of thousands, if not millions of years to accumulate, and then we suck it up to, water our plants and all that stuff, right? So groundwater exists throughout California, but it's not what it once was. And so if you do have a well, it also doesn't mean that like you're doomed and like people still can survive with this stuff. But with the amount of people here in Southern California, groundwater ain't gonna cut it, right? We need something else. And for us, here in the AV, that something else is entirely the California aqueduct. It's not the only aqueduct we have in the state. And like Los Angeles has, a couple of these things. It's relying on this water from the California aqueduct, which, by the way, that's why we have access to it. It's not that we, made this giant thing just so people could live in the Antelope Valley. This exists because of Los Angeles, right? Trying to build up LA, as well as the Los Angeles aqueduct and all this other stuff that feeds into that city. But we benefit because we have this artificial river that flows, right through town. And so this is where most of us are getting our water from, right? The California aqueduct. And this thing is, I mean, it is amazing. And this goes into like why when we have a drought, we don't even pay attention to it. Because look, we can turn on the faucet, water's going to come out because it's being shipped from Northern California down here. So we don't really care about rain here in the South because, you know, hey, it'll keep dust down and all that, but we're still going to be able to have water because it's going on this incredible journey. And when you think about it, I mean, it is amazing what this thing does to bring water here. Right? And so case in point, like Sacramento, California, their elevation is about 25 feet above sea level. Right? Bakersfield is about 400 feet above sea level. So to go from Sacramento to Bakersfield, which is what the aqueduct is doing, it's traveling uphill, right? Not a significant, it's not like you're climbing a mountain. But, you know, if you're moving from Sacramento to Bakersfield, just by default, you're going uphill. That's one thing to do that in a car, but water cannot freely flow uphill, right? Gravity pulls it downhill, which means, you know, it's not like we just dug a trench and this thing comes our way. What it means is we're actually pushing this stuff uphill its entire journey, right? That's cool from an engineering standpoint. That's also expensive. And so not only is it one thing to go from, say, Sacramento to Bakersfield, but once you get south of Bakersfield, you run into mountains, right? Which is what we see here. So we have the transverse range that's the Tehachapis and the San Gabriels and the San Bernardinos, all these things that run, you know, kind of perpendicular with the coastline of California, if you want to think of it that way. So it hits these mountains, and what we're seeing here in the distance is this pumping station where this whole aqueduct, all of the water, gets pumped up a mountain. Right? And what's crazy about this, like, okay, yeah, again, from an engineering standpoint, you know, nerdy engineers high five and like, we did it, we conquered gravity. That's super cool. Here's the problem though. This right here, like this alone, is the single greatest energy user in the entire state of California. Right? This is why we ain't got no money, because our electricity bill is so high. Yeah, we're pushing a river up a mountain. Cool. But we can't stop doing that. Like, we have to do that constantly. We can't take breaks from that because it means we don't have water here, right? So this is an incredible expense. I'm going to be honest, this is the stupidest thing ever. Ever. Yet I will defend it until the day I die. Why is that? Why am I so gung-ho for the aqueduct? Because I own property in the Antelope Valley. I have a house here, right? The minute we stop doing this, the minute the state goes like, you know what? You're right. This is stupid. This place becomes a ghost town because the Antelope Valley, we have way too many people here for the naturally existing water that we can find, right? Like, we don't have Palmdale, Lancaster, and the surrounding communities. They don't get to this size without that aqueduct. So it's stupid and it's a trap. Like, we're stuck with it because we've gotten to this point. So we've got to keep it going along, right? So that's something to think about, but we don't think about it because, again, we don't, think about like what the aqueduct really is. We just turn on the faucet, water comes out. Or if you go to the aqueduct, like you guys do this, right? You Antelope Valley kids, I know, I get it. Like, if I grew up here, it's what I would have done. Like, that's where you go to, smooch and do all your drugs and all that stuff, right? You go up to the aqueduct, right? Of course. It's where I'm sure my kids will do them. When they get to a certain age, I'll make sure I tell them that would be the best place to do it. But when you're up there, smooching and doing your drugs and all that, do you ever look into the aqueduct and go, God, that looks delicious. Man, I just wish I had a big straw. So from here, I could put the straw in there and just drink up that water. I'm so thirsty from doing all my drugs. Yeah, I want to drink out of the aqueduct. You ever think that? No, right? And we know it's, not only do you have fish and ducks and stuff swimming around and they're pooping and doing whatever, but like, you've seen the stories, right? Every year we'll, pull up like, 4 human bodies pulled out of the aqueduct outside of Quartz Hill, or whatever. There are cars and just all sorts of industrial things. Like, it is the grossest, dirtiest water ever. And you're telling me that's what we're drinking? Oh, yeah. And in fact, if you do drive up and down I-5, if you're lucky, you get some really good signs. Like this one here. I forget exactly where this was. It was at some, stop, like near Fresno or wherever, fueling up, getting some gas to continue my journey. And so I saw this sign, aqueduct water is Delta water. Why are Sacramento and Stockton allowed to dump their sewage into the Delta/aqueduct water? Gah! Is that true? Are the Sacramento people, are they putting their poops into our drinking water? Yeah, they are. But here's the good news. It's chemically inert. Right? It's like they've taken their sewage, their little poopies, and they've zapped it to kill all the gribblies or whatever. So yeah, they're putting poop into our drinking water, but it's not like it's dangerous poop. It's just plain poop. Does that help? Now you can drink it, right? It's totally fine. What I do love about this, well, I mean, this is just how we humans have learned to deal with sewage, is just, again, throw it into the water, right? I don't know where this comes from, what our attitude is, where we're like, this water seems important. It's the only thing that will keep us alive here. Let's put all our junk into it, right? I don't know, but it's something and I say we, I shouldn't even say we, it's something white folks have done, right? Because there are plenty of other people who are smart enough, like, our indigenous Americans who were smart enough not to poop in their water. So there you go. Again, something to think about. But here's the deal. Like, don't worry about this, baby. Don't worry about the dead bodies and the poops and all that stuff, because we fix it. We fix this water. We treat the hell out of it. And this, I'm not going to test you on what's, step 7 or whatever. This is just something. It was in the Antelope Valley Press years ago. I pulled it because I think it's a useful thing, and it's a good thing for us to be aware of, because this is our drinking water. This is where our life is coming from here. So yeah, we've got this filthy, disgusting aqueduct water, but we invest millions of dollars a year in keeping it clean. And that's just, us here. But anybody else along the aqueduct that's using this water is doing the same thing, right? But here you can see step 1, we have these intake screens. Aqueduct water is strained to eliminate fish, moss, and debris. And I like that, because debris means, Sacramento poops and dead bodies and car parts and stuff like that. But we have, a fence there. So all the yucky stuff, the really big yucky stuff, gets stuck there. And so we just have filthy water come in here, but it's pumped and, chemicals are put in. And so we're capturing all of the nasty stuff in here. So by the time it gets out here to be pumped back to, our houses, right? It's some of the cleanest water out there. Like, it's pristine, it's wonderful stuff. It is free of anything that could kill us, right? We don't have cholera outbreaks and stuff like that here in Southern California because we're spending millions of dollars to ensure that that doesn't happen, right? The stuff we see in developing nations and all that. We spend a lot of money on this. And what I love too is that, the water companies will send you the postcard that says, yeah, we're going to have to raise rates. Your water bill will go up $1.50, every 2 months or whatever. And we go, outrageous. We pay so little when you think about what goes on with all this stuff. And honestly, what we're not realizing is that this is our tax dollars at work. It's not just your water bill. It's a lot of our taxes go into this stuff. And because of our trying to beat geography, and we get all the rain up north, but we wanted to put all the people down south, because of our effort to do this, well, here we are, right? And that's why we don't have more money going into this thing or that thing or whatever. But just, we should be aware of it. We should be aware that our water is clean. It's you should be drinking from the tap. You don't need to have bottled water unless you're in a house that's older, that has older pipes or whatever. But any of that contamination, for the most part, again, and this is coming from the aqueduct. Because if you're out in some of the outskirts and you're using groundwater, that contamination is coming from the Air Force. And that's, that Aaron Brockovich stuff. That's a different story. But honestly, this water is pristine when it leaves these places. And then any contamination is going to be like your pipes themselves, right? Which is something to also be aware of. But if you're in a relatively modern house, you should be good, right, with this stuff. So be aware of that. And then also, we should be aware of, is that there's no guarantee that water will continue to flow down here to Southern California. Here's another sign from I-5. Look, guys, if you're not driving up and down I-5 just to look at the signs and read all the political stuff all over the place, you're missing out. This is good stuff. You quite often will see me pulled over on that interstate, simply taking pictures of what farmers have put up because it's fascinating. But this was, years ago when up north they decided we got to slow down on the water that's coming down south. It had to do with ecosystem issues. That's another story for another time right there. But a lot of people saying like, oh, these tiny little fish are more important than working farm families and all that, which is not what the case is. But it was a good reminder that, this water isn't a guaranteed thing. It's not always going to be flowing, so we need to be aware of that. And again, conservation, being smarter about what we're farming and where and all of that. That would be the good conversation to have. It's not what we have. And we can say too, I've got plenty of complaints about, the systems we have in place. We're doing pretty well, though, here in the United States in general, in terms of, clean drinking water. Although, honestly, this more than 90%, well, first off, more than 90%, the fact that it's not 100% is an issue, right, in the wealthiest nation in the world. But also, this map came from, before stuff like the Flint crisis and some of these other issues in other poor cities around the country. We're not perfect, but there are places that are way worse off, right? And again, this idea of drinking water like that, I see no problem in saying that clean drinking water should be this human right. It is something that should be in existence out there, but clearly it isn't. And if you want to get to the bottom, I've been talking for a while here, you want to get to the bottom of some of this stuff, again, that's Geography 105. That's the cultural stuff. We talk about rich countries and poor countries and the why, and all of that. This stuff, I'm getting tired. This stuff, I'll end with this stuff. It is good to know, what your water footprint actually is, meaning how much water do you use, right, in a, daily thing. And you can think, well, I drink, 4 8-ounce glasses a day or whatever. I take a short shower, that kind of stuff. But one thing this last drought really made us pay attention to is the fact that water, what you're drinking or taking a shower with or whatever, that's not it for your water consumption. The food we eat is taking water, right? It's using water. Like a cow, that delicious cow. You look at that cow, don't you just want to eat that yummy cow? Well, hold off, because cows use a ridiculous amount of water to, live, as well as the production and all that of beef, right? So what this image is showing here is every 1 pound of beef requires about 1,800 gallons of water, right? And it's getting into exactly what's happening here. So you buy a pound of, hamburger or whatever at the store. When you're doing that, you're using about 1,800 gallons of water for that one little purchase. Now, one thing to be aware of, and this is one thing that drives me crazy, this is why the world would be better if geographers ran it, is that when this stuff was coming out, nobody got into, but where is the beef coming from, right? This sure is an issue if you're sourcing local beef here in, say, Southern California, because that's, that water is coming right out of our spot, or even Northern California coming out of the aqueduct or whatever. But if we're importing it from a place where they've got plenty of water, well, then it's not necessarily a bad thing, right? Now, there are other issues with eating beef, and we'll talk about that. But it's something to think about. Just because having that hamburger or whatever is very water intensive doesn't necessarily mean that's a problem, right? Does that make sense? So think about that. But let's say, and then see, this also gets into issues of shipping of food and carbon emissions and climate. Like, it's a very complicated thing. So let's just say, look, beef is problematic, which it is. It's delicious. Ain't gonna lie. I'll be talking about that more when we get into ecosystems and stuff like that. But it is a problematic thing. But we can switch the types of meat we're eating. Let's say you can't go full vegetarian, right? Because it's hard. It's like giving up smoking or whatever. So okay, just don't eat beef. How about goat? Huh? Because a pound of goat burger, that'd be 127 gallons of water. Way less, right? Eat some goats. I can't do it. And it's water wise and all that. I don't know if you've had goat. I don't like it. And it's nothing wrong with eating goat. I mean, it's not like you can say that, eating cows is normal, but goats is weird. No, it's a cultural thing. It's because I'm, from California and not from, the Middle East or someplace where you have more goat consumption, India or wherever. But this actually, goat makes way more sense. We should be raising goats in California as opposed to cows, right? Just like based on that. Again, it's a spatial issue. But let's say, okay, can't eat goat because it doesn't taste right if you're an old man like me. Chickens. Well, that's kind of meeting in the. It's not quite as water wise as goats, but it's definitely not as bad as beef. Do the chicken option, right? Like, this is stuff. These are the steps we can do. And I also love like all the images right here that they're showing. You start with, a big cow and a big goat, and we didn't even get into pork and all that stuff. But the chicken, they show a little baby chick. Like, that's what a chicken nugget is. It's just a little baby that you eat. Yeah, the image doesn't quite work. But this is what hopefully this makes sense. What I'm getting at here is that here's your big takeaway. Water is crucial to life. We need it. You cannot survive without it. There's no substitution for it. We have plenty on the planet, but it turns out we rarely have it exactly where we want it to be, right? So we need to protect it. We need to be aware of where it is, how it moves, what goes on, what can change the water supply and all that. We need to be aware of these things. And if we don't do that, what hope do we have, right? So here in California, one of our big priorities should be, in addition to, racial issues and Black Lives Matter and the stuff that we're seeing right now as I'm recording this stuff, absolutely, these cultural, social things we need to be discussing. But another thing, and, we can multitask. We can focus on a few things at once. And sometimes these things do go hand in hand, as we may or may not see in the upcoming lectures here. But, we need to be focusing on water supplies, clean water, responsible use of water, conservation of water here in the state and around the world. All right? There you go. There's some uplifting discussion about how we're all going to die of thirst. All right, we're good. Here, next time, we'll get into the atmosphere and some basic weather stuff. I'd love to say it's going to be more uplifting, but I'm going to talk about, sunburns and skin cancer and toxic radiation and stuff like. Hey, don't miss it. It's going to be great. All right, folks. Have a lovely rest of your day or evening or whenever you're listening to this, and I'll talk to you again soon.